Hi, everybody, and welcome back to this Hanson Math YouTube video. In today's video, this is example 3. This is a continuation of section 4.2 in the AP Calculus AB curriculum, which is straight line motion, or sometimes called rectilinear motion. And this is definitely a cool calculator active problem involving a bug moving along the x-axis, and you are given a velocity function. It says here that the velocity v of t is equal to t squared times sine of t cubed minus 1.5t. Okay, with the velocity function given, and for a courtesy, here's the picture of what that velocity function looks like. Domain restricted, we only care about time 0 to 2. So we're only going from 0 to 2 on the x-axis. We're going to be asked a battery of questions. So to do this, I'm going to migrate over to my TI-84. This is the last time I'm going to show this screen. So if you want to look at these questions, you could either take a screen capture and print it out, or you can use the link to this file, which will be located in the description below. So without further ado, we're going to transition over to the TI-84, which is our calculator of choice. And on the TI-84, which should be on the screen now, we're going to plot this function into y1. So y1 equals x squared times the sine of x cubed minus 1.5x. All right, now a couple things just to be certain. Since this is a trig function, it's a sine function, we got to make sure our mode is in radian. So just to check that, I'm going to click mode, and indeed we are in radians, so that is good. All right, so since we're in radians, we're good. I'm going to hit window. On window, I'm going to make sure my x min is 0 and my x max is 2, because that was the domain restriction for this example. And my y min and y max, negative 10 to 10, is probably fine. Let's take a look. So if we hit graph, that's what it looks like. I will notice there is a lot of dead vertical space, a lot of white space above and below. So I am going to alter a little bit, go back to window, and I'm going to make my y min negative 5 and my y max 3, and see if that gives us a little tighter look. And it will. Okay. So this is the picture of the velocity function, and it looks great. So now what I'm going to do is this. I'm going to take my writing implement here, and we're going to put question A at the bottom. Question A said, find the acceleration at time 0.7. Find the acceleration at 0.7. So we're looking at the graph of velocity. This is a graph of v of t. So what is the link between velocity and acceleration? Acceleration, a of t, is the first derivative of velocity. So it's v prime of t. So we're looking for a of 0.7, which means v prime of 0.7. So since we're looking at the graph of v, we want the slope at 0.7. So we can definitely use the technology to do this. Since we're looking at v of t, but we want v prime, let's just use the derivative feature. So the derivative feature is pretty much everything's in the calculate menu, which is second trace. So to get into the calculate menu, we're going to hit second trace, and the derivative is choice 6. dy dx is choice 6. So if you hit 6, now we have to tell it where to look. We want to look at 0.7. So if we literally just type in 0.7, enter, it says dy dx, the slope or the derivative is negative 0.9205. Okay, so that is the answer to this. It says a of 0.7, which is the derivative of v at 0.7, is equal to negative 0.9205. 0.05, which I'll round to negative 0.921. Okay, and you can tell here if we were to draw a tangent line, that's definitely a negative slope, so it fits. Okay, so the velocity, the derivative of the velocity, which is the acceleration, is negative. So we have negative acceleration. So that answers that part of the question. But the second part says, is the bug or the object speeding up or slowing down? To answer the question of speeding up or slowing down, we have to look at the acceleration and the velocity. So we also have to look at what is the velocity here. So the acceleration at 0.7 is negative 0.921. The velocity at this same timestamp, the velocity at 0.7 is, well, it's just your y value. Since this graph is v of t, it's just the y value, which is right here. So it says the velocity is negative 0.318. If you're using an older software calculator that doesn't show this, you could do the following. You could hit calculate menu, which is second trace, and you could go to value. Value is option 1. And you could tell the calculator to tell you what is the velocity at time 0.7, and it will tell you it's negative 0.318, which we already knew from the other screen. Okay, so the headlines here, the headlines are that the sign of the velocity is negative and the sign of the acceleration is negative. They're both negative. So the fact that the acceleration and the velocity have the same sign is evidence that the bug is speeding up. Speeding up is when the signs are the same. So when the signs are the same, an object is speeding up. When the signs of V and A are opposite, they're slowing down. So again, since the velocity was negative and the acceleration was negative at the same timestamp, that is evidence that the bug is speeding up at t equals 0.7 because the velocity at 0.7 and the acceleration at 0.7 have the same sign. Okay, that's your justification. They're both negative or they have the same sign. V and A having the same sign is evidence that the particle or the bug is speeding up. So it's like it's going to the left and being pulled to the left. So all the forces are going left, which is speeding up. Okay, that was question A. I'm going to erase now and we'll tackle question B. Question B says, find any values of t in the interval, just in the interval between 1 and 2 when the bug is at rest. Okay, where is the bug at rest? Well, the definition of at rest is when the velocity is equal to 0. No velocity means you're not moving, thus you're at rest. So where on here is the velocity 0 between time 1 and time 2, which would be somewhere right in here? Well, the velocity is 0 right here and right there. Well, without guessing, how do we find those exactly? You use the calculator. So again, most things are in the calculate menu, which is second trace. And we're looking for where the graph crosses the x-axis, which is a 0. So 0 is option 2. It's going to ask you for left bound. Left bound means you bring the cursor clearly to the left of the x-intercept here. You click enter. Right bound means you move the cursor clearly to the right of where you're looking at this 0 or x-intercept. You hit enter. And guess means you put the blinker right where you think it should be, enter, and there is your 0 or time when there's 0 velocity, meaning the bug is at rest. And that time is 1.224 or 1.225. Okay, however, there's another time when the bug is at rest over here. So the bug is at rest. The bug has positive velocity, so he's moving to the right. The bug is moving to the right. And then the bug takes a break, takes a quick rest right here, and then starts heading negative velocity, which means to the left. So we have to find what time this is over here. So we'll repeat. Second trace 0, which is option 2. Move the blinker over. Okay, left bound is to the left of where it crosses the x-axis. Enter. Right bound, move the cursor to the right of where it crosses the x-axis. Enter. And guess, we'll put it right on target. Enter. And there it is, our other 0 or x-intercept or time when the velocity is 0, meaning the bug is at rest, is 1.801. Okay, so 1.225 is here, 1.801 is here. That is question B. Okay, this was question B. Okay, next we're going to do question C. I don't have to erase anything. Question C says, find the open intervals on the interval of time from 0 to 2 where the particle is moving to the right. Well, the definition of a particle moving to the right is the velocity is positive, which means greater than 0. We're looking at the graph of velocity. This is v of t. So the graph is greater than 0 or positive from here all the way to here. So these are the times between which the bug is moving to the right. So the bug is at rest here, moving to the right as time goes on, moving to the right, and then stops, and then starts going left. So we just found those two timestamps here and here. So to answer the question, we can say the bug is moving to the right, open interval from 1.225 until 1.801. Okay, that is part C. That's the open interval when the bug is moving to the right. Okay, final question D. Find the acceleration of the bug when the velocity is -1. All right, I'm going to erase. So keep in mind, we are looking at the graph of velocity. Okay, this is velocity versus time. Okay, so we're looking at the graph of v of t, velocity. And it says find the acceleration when the velocity is equal to -1. Well, the velocity equals -1. If I trace the -1 line, it's somewhere in this area. But how do I find it exactly? The easiest way to do that, in my opinion, is to do the following. Go back into y equals. Go back into y equals and set y2 equal to an output of -1. So that's looking for where is the velocity -1. So now if you graph this, it's going to plot a horizontal line, every place with which the output is -1, and where they intersect right here is indeed the time in which the velocity is -1. Okay, so again, we're looking for where is the velocity equal to -1. That's right here. So to find the x value or the time value when that happens, we'll use the intersection feature, which will be second trace intersect is 5. It asks for the first curve. To me, all you need to do is bump over the cursor until where it looks like they intersect by I, and then power through with enter. Enter, second curve, we're still right there. Enter, guess, we're right on the money. Enter. So there we have it. The output or the velocity is -1 when the input or time is 1.8368. We'll call it 1.837. Okay. Now, that wasn't the question. That was just the time in which the velocity is -1. The question says find the acceleration at this time. So the acceleration at this time is acceleration at time 1.837. So the connection between velocity and acceleration is the derivative of the velocity. So since we're taking a look at the velocity graph, we also have to find the derivative there to get acceleration. So to get the derivative, we're going to go to calculate menu. Second, calculate derivative is dy dx, option 6. My cursor is exactly where it needs to be, I think. No, it looks like it moved a little bit. So I'm going to press 1.837, 1.837, and we get a derivative of negative 28.876 or 877. So the derivative of velocity is acceleration. So the acceleration at 1.837 is negative 28.877, which makes sense because if you were to look at the slope right here, it is very, very steep and downhill negative. So that tends to make sense. The answer would be something of that magnitude, negative 28.877. All right, so y'all can do a whole bunch of things with these TI-84s, most of which is in the calculate menu, which is second trace. You can find intersections, derivative, mins, maxes, zeros, lots of stuff. Okay, this video is a good one for reference. I hope this helps, and good luck with your continued studies of the derivative in calculus. Have a great day, and we'll see you next time.